Hi. So we've been talking about max-min problems and how important they are. And usually in those problems, we had one dependent variable that we were trying to maximize or minimize, and we had one or two independent variables. Well, we always had to get it some kind of relationship, so we only had one independent variable. Then we took the derivative, and by setting that equal to 0 or undefined, basically we were finding where the slope was such that we might have a maximum or minimum. When we were doing the problem in the last video about maximizing the area that we could cut out of a semicircle of gold, we were always taking the rate of change of the area with respect to one side of the rectangle. And when we later did another max-min problem where we were trying to maximize the profit that we would make when we were producing widgets, we were taking the rate of change of the profit with respect to how many widgets we made. So the with respect to becomes pretty important in derivatives. And neither one of those with respect to's is like when the first example I gave you about using derivatives, when my wife and I went for a walk and we were finding out how fast we were going. So we were finding the rate of change of position with respect to time. And even though the max-min problems didn't have time as our independent variable very often, time really, if you think about it, is probably the biggest independent variable that we'll use, because rates in our world often have to do with per second or per minute or per hour. So time is really going to be often our independent variable when we're taking derivatives in a real world problem. And that's what we're going to be discussing in the next couple videos, is because we're talking about a new type of problem called related rates, where something is changing at a rate, and we're trying to find the rate at which something else is changing, and these two things are related to each other. So again, this is one of those things where I don't really have to teach you anything new that you haven't already learned, so we can go right to solving some problems. So I've got 5 problems to do. Let's see if it makes sense as we go through them. So, just about every calculus book you could ever pick up has the sliding ladder problem in this chapter. So we have a 13-meter ladder leaning against a wall, but starts slipping. So often a picture is really helpful in these. So if I make my wall and I put in my ladder, and this ladder is slipping out, so that the base of the ladder right here is, by the time the base is 12 meters from the wall, it is slipping away at the rate of 5 meters per second. And we want to know how fast the top of the ladder is slipping down the wall. So usually what you do is you look for variables. Well, as the ladder slips, this distance right here between the top of the ladder and the ground is going to change. So we could call that a variable. Also, as the ladder slips, this distance is going to change. But the ladder is a constant, so we don't really want to add another variable. So there's our picture with our variables and our constants in it. What are we trying to find? We're trying to find how fast this top is slipping down. So we're trying to find the rate of change of y. With respect to what? Well, now, with respect to time. So what we're trying to find is dy dt. And what do we know? We know the rate at which this top is slipping away, so we know the rate at which x is changing. It's getting bigger by 5 meters per second. So we could write down that dx dt equals 5 meters per second. And it's getting bigger, so you want to keep it as positive. So we need some kind of relationship. These are related rates. We have a nice relationship here. Pythagorean's theorem says that x squared plus y squared equals 13 squared. And we're trying to find rates with respect to time. So the only way we can do these is to take the derivative, and we want to do it with respect to the independent variable time. Now you have two choices. We could solve for y and take the derivative explicitly, or we can just start taking the derivatives implicitly. That would be my choice in this case. So let's see how easy that is. The derivative of x squared with respect to x would be 2x. But we have to remember, we've got to do the chain rule. X is a function of t. So what we really have is some function squared. So the chain rule would say 2x times the derivative of x with respect to t. So dx dt. And the derivative of y squared, y is also a function of t, so the chain rule would say 2y times dy dt, and the derivative of a constant, 13 squared, is just 0. Now you could divide everything through to get rid of the 2's, and then we just plug in numbers. Hopefully we only have one unknown, which we're trying to find. So we're trying to find dy dt, so that's going to be an unknown. But what do we know? It says by the time the base of the ladder is 12 meters from the wall. So at this time, x is going to be 12. And we need also y. Well, if this is 12 and this is 13, we have a Pythagorean triple here. That's going to be 5. And dx dt, we've already said, is a positive 5. Well, this is actually going to be some pretty easy algebra. 12 times 5, 5 times negative 12 is going to equal 0. So dy dt is a negative 12, and the units would be the same units. They would be meters per second. Now, as a technicality, the answer wouldn't be negative 12 because it says how fast is it slipping down the wall. Well, the length is changing by a negative 12, but the height is slipping down by 12. So you'd say it's slipping down at 12 meters per second. And we've solved A. Now for B, they want to know how fast this area in here is changing as it slips. Well, now we want to find what? We want to find dA dt. Is there a relationship we know? Yeah, this is a right triangle, so we know the area equals 1/2 the base, x, times the height, y. Now we don't have to worry that there's two independent variables because we now know both dy dt and dx dt. We can only have one unknown rate. So we're ready now. That doesn't do us any good. We want to do rates. So we have to take the derivative with respect to time. So we would say dA dt equals 1/2. And now we have to do the product rule. So we go x times dy dt plus y times dx dt. What we're trying to find is dA dt, so hopefully we know everything here. X we said was 12. dy dt we just found to be negative 12. Y is 5, and dx dt was 5. So altogether you get negative 144 plus 25. dA dt is negative 119 halves. And this is area, so it wouldn't be meters, it would be square meters per second. And that would be how fast the area is changing. It is changing at a negative rate. The area is getting smaller as that ladder, as you see, as that comes out down like that, the area is getting smaller at this point in time anyway. Now, the last thing they ask, how fast is the angle between the wall and the ladder changing? Well, here's the wall and here's the ladder, so this is the angle, so we need a variable name. And we need a relationship. Well, especially if we hadn't already done A and B, we already know something about the rate at which x is changing. So I would probably use x and a constant. So the opposite of the angle and the hypotenuse is, you'd want to use the trigonometric relationship, the sine. So you could say the sine of theta is x over 13. And now we can just start taking derivatives implicitly with respect to time. So the derivative of the sine of theta is cosine theta. If you were just taking it with respect to theta, but you're taking it with respect to t. So we have to remember again to do the chain rule. We have to say it's the cosine of this function, then times d theta dt. We have to finish the chain rule. And the derivative of 1/13 x is 1/13 times dx dt. Now the only thing, hopefully, we don't know is d theta dt. We know that dx dt, the rate at which that's slipping out, is still 5. And what's the cosine of theta when this is 12? The cosine would be 5 over 13. Wow, doesn't that work out nice? 5/13 times this is equal to 5/13. So d theta dt is just equal to 1. Now this is where you have to remember when we did all our formulas for derivatives of trigonometric functions, the formulas all were done in radians. So this is 1 radian per second, which is changing at a pretty fast rate when you know a radian is getting close to 60 degrees per second, that's changing. And that would happen as the ladder is falling. Okay, so let's go to a completely different problem. In an electrical circuit, the voltage is increasing at 2 volts per second, and the current is decreasing at this many 1/5 amps per second. At what rate is the resistance changing at the time that the voltage is 10 and the amperage is 4? So again, this is related rates. We know the rate at which the voltage and the current are changing, and we're trying to find the rate at which the resistance is changing. And there is a relationship in an electrical circuit between those three variables. And it's called Ohm's law, if you remember from science. So Ohm's law says the voltage equals the current times the resistance. So we've already got our relationship. We don't have to come up with any kind of new laws if we know Ohm's law. And now this is kind of useless to us because we're trying to find rates with respect to time. So what we have to do is take the derivative with respect to time. So we get dv dt, and then I and r is a product, so we have to do the product rule. So we go I times dr dt, the first times the derivative of the second, plus the second times the derivative of the first. And we just have to hope that the only thing we don't know is dr dt. That's asking for quite a bit. Let's see if we've got everything else. Well, the voltage is increasing at 2. So this would be a positive 2. The current is decreasing at 1/5. So the current is negative, di dt is negative 1/5. So now we need R and I. Well, it says right here that the voltage is 10, but there's no V there, and the current I is 4. So we know this is 4, but we don't know what R is. But we do have this relationship. So if the voltage is 10, and the current is 4, we can find out at this point in time in the circuit, the radius is equal to 10/4, or 5 halves. So at this point, we should be able to solve for dr dt. So if you cross out the 5's and bring this negative 1/2 to this side, you get 4 dr dt equals 2.5, or 5 halves. So dr dt is equal to, if I divide by 4, 5/8. And what would the units be? If you know electrical circuits, resistance is in ohms. So this would be ohms per second. And that would be how fast the resistance at that point would be getting larger. The voltage is getting larger, the current is getting smaller, and the resistance is getting larger. So good. Let's try another one. Maybe if you were a chemical engineer, you'd be interested in a problem like this, because they deal a lot with the movement of petrochemicals from tanks into processing areas. So in this case, it could be a petrochemical. I've got it just as water. Doesn't really matter. It doesn't change the math in this. So we have a conical tank with the vertex down. That makes a difference if the vertex is up or down. So we probably want to draw our conical tank. And what do we know about the conical tank? The base diameter is 100 meters. Well, we don't use diameter in most of our formulas, so I'm going to say the radius must be 50. So I can go right here and put 50 for the radius, and the height is 10 meters. So I'm not too to scale here, but my math should take care of that. And I can draw that height in like that, but I also have to put the water in my picture. So I'm going to put some water in here. And what do we know about the water? It's going to have a radius and a height of that water. And we know that water is flowing at a rate of 25, so it's actually coming out of the tank, maybe going into some processing plant at 25 cubic meters per minute. So what we have is, this is cubic meters per minute. So this is dV dt. And it's the volume of water is getting less, so it's actually going to be a negative 25. And what are we trying to find? How fast is the water level falling? So we want to know how fast this H is changing. So we want to find dH dt. So we need a relationship in this water between the volume and H. And if you remember from geometry, we have that relationship. The volume is 1/3 pi r squared h. We know dV dt. We're trying to find dH dt. The only problem is, if we take derivatives, we're going to get a dr dt. And we don't know anything about the rate of change of the radius. So what we need to do on this problem is find a relationship between r and h. And I'm hoping you can see the similar triangles. This big right triangle and this little right triangle. So we can say 50 is to 10 in the big triangle as r is to h. Well, 50 is to 10 is just 5, so you get r equals 5h. We have a nice relationship here. So in place of r, I can plug in 5h. And I can simplify that. Altogether, the volume is going to be 25 pi over 3, and we have h squared times h is h cubed. Now we've got a relationship with just those two variables, and we know the rate at which this is changing. So now we can take the derivative with respect to time. The constant just stays there, and the derivative of h cubed is 3h squared times dH dt. So unless the variable is actually time, you always have to do the chain rule in these problems. You just know that h is a function of t. Well, we can cancel out the 3's, and now we plug in the numbers. dV dt is negative 25 because the water is flowing out. And h, we want to do this when the water is 4 meters deep. Well, I think we can now solve for dH dt. We could cross out divide both sides by 25, and now we get dH dt is negative 1 over 16 pi. And the units are going to be what? It's h, so it's just meters per minute. So it's negative. So to answer this question, you would say it's falling at a positive 1 over 16 pi meters per minute. Well, now we have to know how fast the radius of the surface area is changing. So what am I going to have to do? Am I going to have to go back and, instead of solving for r, solve for h and go through this whole thing again? It kind of looked that way, but we're running out of room. So we have to use our head and say, is there some other relationship that we found? Oh, look at down here. That's a much simpler relationship to use than this. And I already know what dH dt is. So all I have to do is say dr dt is 5 times dH dt, which we already know. So we would say dr dt is negative 5 over 16 pi, and it's going to have the same units, meters per minute. So that's negative because it's getting smaller. The height is getting smaller, the radius is getting smaller as the water is flowing out. So there's probably somebody watching this that might want to become an engineer. This is the type of problem you'd be dealing with. Also, if you're 6 foot tall and you walk around streetlights, you might be dealing with this next problem. We've got a man and a streetlight and a ground. So there's the ground. Here's the 15-meter streetlight, and here's the man who's 6 foot tall. And what else are we talking about in this picture is a shadow. We want to know how fast the shadow is changing. So we probably should also put in the light beam that makes the shadow. So here's the top of the light. This is going to be the shadow. And we want to know how fast that's changing. So we better call it a variable, x. This is not a variable. That's a street light, and this is a man. Now the other thing that's changing, and we want to put this in there, is the man is walking towards the street light. So as he walks, that's the rate at which this distance is changing. So we better call that a variable. And what do we know? We know that dy dt, it's negative because it's getting smaller, and he's walking at a rate of 3 feet per second. So that's what we've got to work with. What are we trying to find? We're trying to find dx dt. We need a relationship between x and y. And your first thought, with all these right triangles, the Pythagorean's theorem might be the way to go. But we know nothing about the hypotenuse. So we don't really want to throw another variable in there. So we think back to geometry and we see we've got right triangles. So they should be similar right triangles. So they should be in proportion. So we can say 6 is to 15, which, by the way, you can reduce to 2/5 as 6 is to 15 as x is to x plus y. You can either do it that way, or you can go 6 is to x as 15 is to x plus y. Same thing. Now, at this point, we've got a relationship. And if you wanted to, you could right now take the derivatives of both sides with respect to time. But then you're dealing with a quotient rule over here. So we're always allowed to simplify before we start. So I think I would do that. I'd cross multiply and get 2x plus 2y equals 5x. And that would be much easier to take derivatives, but I can even go further. I can say 2y equals 3x, and I can even go and say y equals 3/2 x. Actually, y equals 2/3 x, sorry. No, I got it right. Y equals 3/2 x. Maybe I should have done it the first way. My algebra isn't that good. So now I can take the derivative. I can say dy dt is just equal to 3/2 times dx dt. And we're trying to find dx dt. So dx dt is going to be 2/3 times dy dt. And that's -3. So we can see dx dt is just equal to -2, and it would be in feet per second. So, does it make sense that that's negative? As the man is walking here, when he gets to this point here, look at the shadow is going to be quite a bit smaller. So it does make sense that that shadow is decreasing in size. So I'm hoping you see these are all pretty much done the same. So let's try another one. You have a sphere. Maybe I don't even need the picture. I just felt like drawing a sphere. At a certain point in time, the radius is increasing at 6 meters per second. So this is going to be dr dt. And the surface area is increasing at 24 pi square meters per second. So I'm going to call that dA dt. And they're both positive because they're both increasing. So at this time, what is the rate of increase of the volume? So we need an equation that has volume in it that also has the only variable, and the only variable in a circle is the radius. So going back to our geometry, that's the formula for the volume of a sphere. And now we go dV dt, because that's what we really want to find. The derivative of this is 4/3 pi times the derivative of r cubed, which is 3r squared, times dr dt. Again, r is a function of time, so we have to do the chain rule. The 3's nicely cancel. Oh, but what do we not have? We have dr dt to be 6, but we don't have r. Oh, well, should we give up? No, we've got something we haven't used yet. We got this surface area. So we know the surface area of a sphere is 4 pi r squared. So we want to use this piece of information, which is the rate of change of the area. So I'm going to say dA dt. If I take the derivative of this, I get 4 pi times 2r dr dt. So I get 8 pi r times dr dt, and now plug in 24 pi, and dr dt we know to be 6. So we can find out what we needed over here for the radius. We can just take 48 pi from this side, and we get r to be 1/2. So we can find out that the r is equal to 1/2 at this time. So now I think I'm all set to get an answer. And dr dt we said was 6. Well, 4 cancels with 1/4, so we get 6 pi. The only thing that's left is 6 pi, and that would be in cubic units. So it would be cubic meters per second. So we did 5 kind of really varied type of related rate problems. These are so important that I think I'm going to just do a few more tomorrow. If you feel confident with this, you wouldn't have to watch them, but I would encourage you to. It won't take quite as long as today's. Anyway, have a good day.